Hello there, I'm François, software developer from France. In this video, I would like to show you an interesting architecture to build a reliable data ingestion service. The goal here is to implement a service exposing a REST API where we can send documents to index or analyze. However, we want it to be robust enough to handle hundreds of documents per second. To achieve this, we'll consider the web queue worker architecture, which we'll explain in a minute. The actual implementation will be made using FastAPI, the hottest Python framework out there, SQLModel to manage our database models, and Dramatiq, a reliable and easy-to-use worker queue in Python. Before diving into the subject, I would like to present my book, Building Data Science Applications with FastAPI. It's the reference book about FastAPI, and it will give you all the keys and insights to build your very own machine learning systems in Python. With this book, you'll learn all the modern aspects of Python, including type hinting and asynchronous I/O. You'll learn how to build RESTful API using FastAPI, and you'll learn how to build, test, and deploy efficient and reliable machine learning systems. The book is available on Amazon, both on paperback and ebook. You will find the link just below. Now, let's get back to our data ingestion service. Traditionally, REST API validates user input, performs some operations, and saves the data into a database before returning a response. While this is working for most applications, we could hit a bottleneck in the case of our data ingestion service. With thousands of requests per second, we can't be sure our web server will be able to handle them fast enough without blocking, and so take the risk to lose some documents in the process. That's why we'll consider here what is generally called the web queue worker architecture. Basically, the whole application is composed of three things. First, a web server, which is our user-facing API, which will validate user input and send new tasks into the queue. A queue, which will store the pending tasks for later. And a worker process, which will pull new tasks from the queue and handle them in the background. By doing this, we are moving all the heavy logic into a background process, the worker. Hence, the role of the web server is just to validate user input and send new tasks into the queue. Usually, queues use very fast and efficient technologies like RabbitMQ or Redis. Therefore, the operation inside the API is very quick, allowing the web server to answer the request more rapidly, which is highly desirable if we have a lot of requests to handle. The worker process can then process the tasks as they come. Even if there are a lot of them, it's not an issue. Every pending task is safely stored inside the queue. We limit the risk of losing documents in the process. If we wish to handle the queue more rapidly, all we have to do is to spawn more worker processes that will pull and handle tasks concurrently. This architecture may sound complex to implement, but actually, thanks to FastAPI and Dramatiq, you'll see that we can do it very quickly. As the plan. The web server will be implemented with FastAPI. Task management will be handled by Dramatiq. The queue data storage, we say a broker in this context, will be Redis. And finally, the actual documents will be stored into a SQL database with the help of SQLModel. So, enough talking, let's get to the code. Here is the whole project for our data ingestion service. You can find the GitHub repository in the link below. Here are the models for our applications. Those models will be used both for data validation in our API, but also to structure and save data into our SQL database. This is the major strength of SQLModel, the latest library from the creator of FastAPI. The goal was to provide a simple syntax to define data model classes using simple properties and type hinting, but also allowing to define SQL tables and actually save data into a database. So we define two models, document input and document. The first one will be the data structure accepted by our REST API. This is one of the great things of FastAPI. With those kinds of models, the data validation comes for free. If a property is missing or doesn't have the right type, FastAPI will automatically generate a proper error response. Here we define two properties, ID and content, which will be the raw content of the document. We choose here to use UUID instead of a classic auto-increment number as primary key. It's an interesting pattern in this context because the client can set the ID by itself, which may be useful if we need to send, for example, an updated version of the same document. If we relied on a classic auto-increment identifier, the client doesn't know upfront the ID the database will assign to the new document, or we would need to make a new query, which would be more expensive. The second one, document, is the actual data structure for our SQL table. Notice here that we have the argument table to true. It inherits from document input, so we'll have the ID and content fields, and we added two datetime, created add and updated add, so that we can track the different update time of our document, and a category field, which is a simple string. This category will be determined automatically during data ingestion, during the worker process, thanks to a machine learning model. Let's now have a look at the worker code. Basically, it's a Python module containing all the tasks that will be handled by Dramatiq. We also initialize here the various parameters for Dramatiq, especially the broker. We see here that we create a Redis broker instance with all the connection parameters, and we set it on the global Dramatiq instance. Then we have our task definition. Here we have only one, ingest document. It's a regular Python function upon which we added the Dramatiq actor decorator. That's all we need to define a task in Dramatiq. You see that it takes in argument a document JSON. It's a JSON representation of a document input object. Indeed, Dramatiq is not able to work directly with Python objects. Why? Because they need to be serialized, to be saved into the Redis broker before being handled by Dramatiq. So obviously we cannot save directly Python objects. So it's usually safer to pass by JSON because we know that it's a safe representation of the data. That's why here we can parse it to recover here a proper document input object. Then we open an SQL session. It means here that we will be able to make SQL requests to our database. First, we check if we don't have already a document with the same ID. As we said before, we want to be able to update existing documents in our database. So here we check if we don't have already a document with the same ID. If not, we can create a full instance of the document with created add, updated add properties. Otherwise, we just have to update the data with the new one from the input. Actually, the most important step in this function is the category prediction. As we said, we use a machine learning model to automatically predict the category from the content of the document. To do this, we use the category prediction class. This is a utility class which is present in the predict module, allowing us to load a scikit-learn model that has been previously trained in another script and dumped using joblib. The model is a simple multinomial naive Bayes classifier which have been trained on the 20 newsgroup text dataset. The goal here is not to have a very efficient and smart machine learning model. It's just to show you that you can have a very expensive operation like machine learning prediction in the worker process because it is handled in the background, so you can perform very expensive tasks without worrying about the stability of your application. If we go back to the worker, you see that we assign the result of the prediction to the category property. We update the updated date time, and we commit the document into the database, meaning that we are actually saving the data into the database. Let's now see how to implement our REST API endpoint to accept new documents into our service. You'll see that by using FastAPI, it only involves a few lines of code to make it working. The first thing to do is to define a new application instance of FastAPI, and then with this, we can define our API endpoints. The add document endpoint is just here. It's just a simple function, add document, which accepts a document, and you see that we use type hints to tell the type of the document. By doing this, FastAPI will automatically understand that we expect a document which is structured following the document input model. So if a user sends a JSON payload which doesn't conform to the document input model, we'll have a validation error. That's all we need to do. Inside, there is the actual operation we are doing in the API. As we said before, our goal here is to make it very small and quick. So the only thing we are doing is to send a new task into the queue. To do this, we just have to import the ingest document task from Dramatiq, from the worker module, and use the special method send. As we said before, we take care of serializing the arguments into JSON to be sure that the data is correctly saved into the Redis, and then the task can retrieve it safely. And we return the document. And that's it. By doing this, the API endpoint added a new task into the Redis queue, and the worker can then pull it and handle it. Now let's see it in action. As we said before, our service needs 4 things: a web server process, a worker process, a Redis broker, and an SQL database. For local development, we'll use a simple SQLite database, but for the Redis broker, we need a proper Redis server. To do this in local, it's usually easier to run a Docker container. Docker run. I expose the standard Redis port on my local machine so I can access it through localhost. Great. We now have our Redis container ready to use. Now let's run our FastAPI app. To do this, we'll use the uvicorn web server. So I type uvicorn, the path of my app instance, and enter. FastAPI is now running. Let's now run the Dramatiq process, which will be the worker that will handle the tasks. So on another terminal, I type Dramatiq and the path of my worker module and run. you can see here that by default, Dramatiq will run several worker processes, so they will be able to handle tasks in parallel. All we have to do now is to test our API endpoint and see if the documents get saved in the database. So in another terminal, once again, I will make an HTTP request to our endpoint. Host 8000 documents content hello world and enter. You can see here that we get a success response from FastAPI, which returns us the content of our document we just input, and it generated a new UID. Meanwhile, Dramatiq has processed the documents. There is no log here, but we can check if it did its work actually by using another endpoint to retrieve a document by UUID. Let's do it. So I copy the ID. Let's see what happens. You can see here that FastAPI was able to retrieve the document from the database. You see that we have the creation and update date, and also the category that has been predicted by our machine learning model. Obviously here, the category is not very relevant, but it shows you that Dramatiq has done the work in the background. So our application is working in local, that's great, but it will be even better if we deploy it on the cloud so that we can integrate it in a complete architecture. To do this, we'll use Heroku, which is a serverless platform, so we can deploy the application very easily without worrying about set up servers, etc. So here in the code, I've defined a procfile file, which is a special file for Heroku, which defines which processes it should run when your application is deployed. So you see here that we have two. One is a web process, so we use UVcorn here, and another one, which is the worker, which simply runs the Dramatiq process. You see here that for Dramatiq, we use those options which are there to limit the number of processes and threads that Dramatiq launch by default. Why do we do this? Because we'll use hosted Redis by Heroku, and on lower plans, the number of connections to the Redis is quite limited. So if we spawn too much processes, we'll hit the limit of the Redis connections and the application will not work properly. So by limiting here to 16 processes, more or less, we make sure that we don't hit the Redis connection limit. Now we can simply create our Heroku app and deploy it on their platform. So to do that, I've installed the Heroku command line interface, so I can just use it directly. So first thing is to create a new app on Heroku. So I will tell so I give it a name and I specify the region to Europe. Great. So now the app is created on Heroku. The second thing to do is to set a remote Git branch for Heroku. Actually, Heroku uses Git to retrieve your source code and deploy it. So we'll set a special remote so that we can directly send the source code through Git. So there is a command to automatically set the Git remote, Heroku Git remote, and I tell the name of my app. And you see here, it created an Heroku remote which points to the Git repository created for our Heroku app. Now we'll create the add-ons. Remember that we need a Redis broker and an SQL database so that our whole application works. The good thing about Heroku is that it provides hosted services like Redis or PostgreSQL directly out of the box through the add-ons system. You can create them very easily using, once again, the command line. First, we'll create the PostgreSQL database. Add-ons create. Here is the name of the add-ons. And after the column, you can choose the subscription plan you want to use for this add-on. For PostgreSQL, Heroku has a free subscription plan, which gives you a very small database, but ideal for experiments like this. It's called Hobby Dev. And submit. Here. You see here that the database has been created. And now we can create the Redis database. So once again, add-ons create, Heroku Redis, and I choose the subscription plan Premium 0. There is also a free hobby plan for Redis, but I want to show you there how far you can go with the service, how much requests it can handle. And the free Redis is a bit limited in terms of number of connection, etc. So the Premium 0, which is the first subscription plan for Redis, is a bit more powerful. So we'll use this one and submit. The good thing about add-ons is that they are automatically attached to your Heroku app. It automatically sets environment variables, which will be available in your web process, worker process, so that you can directly connect to the databases and other services you might set in add-ons. You can see this if you run the command Heroku config. Here, you see here that it has automatically set two variables, database URL and Redis URL, with the correct credentials to access the databases. Everything is ready. All we have to do now is to push the source code into the Git remote repository so that Heroku can start deploying our application. Just do git push Heroku main. So Heroku is the remote branch and main is my local main branch. You see here that it pushes the source code, and then automatically you see here all the log of Heroku where it starts the deployment. After a few minutes, our Heroku app is deployed and ready to be used. Be careful though, because by default, Heroku only starts the web process. So the FastAPI app is running, but not the Dramatiq worker process. We have to run another command to tell him to scale, to start the worker process. Heroku ps scale worker. So this is the name we defined in the profile file, 1. We put one process. We can test it right now using the subdomain Heroku gave us. FastAPI Dramatiq service.herokuapp.com/documents content hello world and submit. Here is a success response with a proper ID. And right now the document is being handled in the background by the worker process. We can check if it worked correctly by retrieving the document by ID. Dramatiq service. Here it is, with the category, the creation, and update date. It's working on the cloud, and as you have seen, Deploying to Heroku only took us a few minutes. So this is great, but the goal from the beginning was to implement a service able to handle hundreds of documents per second. To test this, I've set up a simple test on the loader.io platform, which is an add-on available on Heroku. And you see here that I've set a test making 250 requests per second. And here is the definition of my request. It's just send a new document to our documents endpoint with some dummy content. So let's see how it goes and run the test. So the test is starting and we see the requests are currently coming to our server. So the test is now finished and you see that our web server was able to handle 15,000 requests in only 1 minute with no timeout and no error. The average response time is only 73 milliseconds, which is really great. So we didn't lose any document in the process. Our web server was able to ingest every document we sent to him. And now the background process is currently working to process those thousands of documents. To convince you that the worker is actually working, I show you here the content of the Heroku database. You see that we have 50,001 rows inside it. The first one being the document I send using my manual request to test. And the other one are the documents from the loading test. So every document have been saved in the database and the category have been predicted using our machine learning model. So this is quite a success in my opinion, given that we only used 3 dynos from Heroku and the first tier for Redis database. So let's imagine what load we can handle with a more powerful server and more powerful databases. This is a great starting point to build a reliable data ingestion service. I hope you liked this video and that it gave you ideas for your next project. If you wish to go further and master FastAPI to build efficient machine learning applications, be sure to check my book Building Data Science Applications with FastAPI, which is available right now on Amazon. The link is below. Thank you for watching. See you soon.